I couldn't resist. So there is this one more example for genus 1, which you could probably see 12 circles, 5 of them horizontal, 5 of them vertical, and 2 more. And this actually corresponds to a fibration that's in some papers written as 5511. So you have 12 singularities and elliptic so the rational elliptic surface CP2 blown up 9 times have really different kind of elliptic fibrations mapping down to the sphere, especially if you allow not just nodal singularities, but more general singularities. And that has been studied by a paper of Miranda and Persson a long time ago, so you could find this paper. But the key idea is that some of these very special fibrations give us really nice singularities and really nice monodromies. And especially if you want lots of nodal singularities lying above the same point, then it's more or less rigid. So here we are looking at a case when we have 5 spheres over 1 point, another 5 spheres over another point, and 1 and 1. So you could, if you want to look at this example, try to do the same thing as for the other example. Even better would be to knowing, I'm telling you there are finitely many of these really nice pictures, not too many actually, so you can try to find them all. The special about them is that you have 4 kind of circles inside, and the ones that we have are always parallel. So this is 5, 5, 1, 1. There are 4, 4, 2, 2. That's another possibility, and 6, 3, 2, 1. Okay, moving on. Genus 2. So last time we looked at a particular genus 2 identity. So this is always going to be a factorization of the identity. And we looked at this A1, A2, A3, B square is the identity. So this is a factorization when all in all I have 6 singularities, or 6 of these Dane twists. 6 of them, A1, A2, A3, and again A1, A2, A3 are irreducible, and 2 of them, B and again B, are reducible. So this has a name. It's called either 2,6 or 6,2, but let's today call it 6,2 factorization. 6, how many reducible? 2, how many reducible? So you have NK. Interestingly, if you don't have any reducible factors, if this is 0 and 0, then there is a result of Siebert and Thiam that tells you that this has to be holomorphic. So if you have no reducible fiber, but if you do have reducible fiber, it may or may not be complex. Sorry. This one comes from actually from a holomorphic fibration. So this is an example. This is a Matsumoto relation, but it comes from an example of Xiao, Gang Xiao. There is a really nice book by Xiao from '85 in French, but it's freely available from the internet, and I highly recommend it. When he actually studies all kinds of genus 2, holomorphic genus 2 fibrations, and constructs a family of them that is parameterized by an integer d greater or equal to 2. D equal to 2 is exactly giving you that kind of identity, and that gives you a 4-manifold as well. So in all the cases, you get several things at the same time. You get an interesting holomorphic, you get a complex surface together with a map, and it is always a genus 2 fibration. In case of D equal to 2, it's actually a nice manifold S2 cross T2 blown up 4 times in a disguise. So the manifold is not that interesting, but the fibration is. And the plan for today is that we are going to actually carefully investigate the d equal to 3 example, which will be, I hope, interesting or at least instructive. And I also worked on the d equal to 4 example, which is progressively harder because it has more singularities and just harder to understand. And I'm working on now the d equal to 5, which is very, very similar. So there is a list of things you can study. As d gets larger, actually the genus also gets larger. So these are the only examples when the base is the sphere. And if you only care about Lefschetz fibrations over the sphere, then you stop here. But if you care about other Lefschetz fibrations over higher genus surfaces, then you can look at the other cases as well. Okay, so maybe I should say, why do we care? I know this manifold very well. I could construct it without ever resorting to a genus 2 fibration. But as it turns out, you can do a lot with that. So there is a paper by Stipsicz and Ozbakci, that does non-holomorphic, that constructs non-holomorphic genus 2 fibrations with a trick that we can learn today. And there are a bunch of other papers much later by Bajkur, Hamada, Akhmedov, for example. And I highly recommend, Akhmedov Mondan, I highly recommend you to read it at some point. But before that, maybe it's worth to try to investigate what you can do on your own and then read the papers. What I mean here is that what we have here already is this manifold given by this genus 2 fibrations, and it's fibers over S2. But you could say, well, let's look at a regular fiber that over that I just have a genus 2 surface. Let's delete the neighborhood of that. Now I have here D2 cross the genus 2 surface. And well, it turns out it's easy to compute the fundamental group of that. If I didn't know this was S2 cross 2 blown up 4 times, I could still compute the fundamental group because it's given us a Lefschetz fibration, so that's an alternative. And then what you could do is try, for example, take 2 of these. So take one copy, take another copy, again delete, and then you have a choice. In fact, you have infinitely many choices because what you have is one genus G surface and another genus G surface, right? And you can identify this genus G surface with genus 2 surface with that genus 2 surface any which way you want, say with a symplectomorphism, for example. And then you can extend this to a diffeomorphism between S1 cross sigma 2 to S1 cross sigma 2, not doing anything exciting on the S1 factor, just reversing the orientation on them. And then you can do the fiber sum. So this is called fiber sum. But you have choices. Even if you want to understand what is the fundamental group of what you get, then it turns out it does matter how you glue things together. What is the first homology of you get, you have choices. Because what happens is that here, the first homology has rank 4 on the genus 2 surface, but some of the things die on the manifold. What are the things that die? These are exactly the homology classes of the vanishing cycles. So actually a half-dimensional space dies here, another half-dimensional space dies there. So if you are not very adventurous, you can just identify these 2 things directly, and you will not kill any more of the fundamental group, and then you would get Z plus Z. But if you're adventurous enough, you do a different gluing, and then you get maybe different homology classes and different fundamental groups. First homology is easier to compute, but you can also realize that there are sections here that intersect the fiber, so you can actually see that the fundamental group will be abelian, so it's enough to compute the first homology to get the fundamental group. So this is a task for you, if you may be more interesting than the first task, is to do all kinds of construction and see what we can construct out of this idea. As it turns out, you could construct, for example, exotic smooth structures on CP2 blown up 9 times, which is already interesting. Okay, so I hope this explains why one could care about these examples, but now we are just going in earnest to look at this more complicated thing and see if we could understand it. So again, there are two approaches here. One is that I give you the relation and you check it. Or we learn how to find these by ourselves, and I hope we can at least make an attempt of how to find these relations ourselves. But for that, we have to start with an actual construction that will use a little bit of complex geometry. I mean, trying to explain that. So we are going to do Xiao's construction for d equal to 3. That you can read in a paper by Akhmedov and Mendon, or you can actually read Xiao's book because he also explains this. So, but in French. So we are working in CP2, and what I'm going to draw is a bunch of lines in CP2, so complex lines. They are determined by a few points. So we have actually 6 lines and 7 points. I think we have 6 lines and 7 points. Okay. This point we really like. So this will be sort of special. And the rest of the points, maybe I could call this A, B, and C, and just not name the other 3 points. Okay. So we have these 7 points. And what Xiao does is to construct a degree 4 hypersurface. This, remember, is just a homogeneous equation of degree 4 in, I guess, 3 variables, right? But he wants a very, very special degree 4 hypersurface, or hyper. Yes, so let's call this D. So if I had something that's smooth, that will be one thing, but he wants a very sort of singular object, a singular object that goes through all the 7 points. But more than that, in around A, for example, so this is the behavior that we should get around A. It will have this nodal singularity. So remember, this is when locally it looks like 2 planes intersect at one point. And around C, it will also have this nodal singularity. And around B, it will also have this nodal singularity. But it also goes through the other 4 points as well. So first thing, we should probably convince ourselves this is possible. We will do that in a second, but okay, so what can we do with that? Okay. The first thing we could do is to blow up where actually you see 7 points blow up everywhere. Okay? So now CP2, so 7 times. So now we have CP2 blown up 7 times. I know at the first it looks like it's just overwhelming, but turns out you can just very slowly really understand what's going on. I'm not sure we will be able to completely go through this, but it's not that hard. So just bear with me. So what happens is that if I actually do that, then these points will be replaced by, remember, CP1s. So almost the same picture, except there will be this CP, this exceptional surface. So there will be this E1 exceptional curve, and there we used to have these 3 things going through, and now remember that this new curve D also goes through this point, right? So the local picture would be something like, like this instead. Is that okay? So this is E1, and some of the similar pictures happening here as well. At this point, only 2 of the curves went through, right? 2 of the lines. But we made sure that this one goes through that point actually twice, right? So when I blow up that point, this will be really still sort of similar. I will have this exceptional curve corresponding to that point. There will be 2 lines going through, and that D will now go through like this, because they used to intersect, but with different tangencies. So after I blow up, these tangencies will no longer be the same. So now this is how it will look like. Are we okay so far? So what do we want? What do I want? A genus 2 fibration. What do we have? Well, not yet a genus 2 fibration. Instead, we have CP2 blown up 7 times, right? But inside CP2 blown up 7 times, I also have various curves. If you want homology classes or embedded surfaces would also work. What are these things? I have originally the lines, but now I blow them up. So the picture of them would be still somewhat similar, but now this would be one of the lines going through E1 once, and some of the other E's as well going through. Okay? So I have a bunch of curves like this, the 6 lines, and I also have D, which is also now an embedded surface inside. Okay? And the next step, so what do you think should be the next step? I could do that, but then I will. So I could be content of working with CP2 blown up 7 times. Turns out the manifold CIO construct is not CP2 blown up 7 times, so we actually have to change the manifold. But then why did I blow up, right? Yeah, I could try that. I can tell you that CIO's manifold secretly is going to be S2 cross T2 blown up 3 times. I really have to do something drastic to get that. The drastic to do is to do a double branch cover. So which is not that bad. For that, one has to double check, and please do, that the homology class represented by the sum of this divisor is divisible by 2. That is some computation. It has degree 4, so you have 4 times the generator originally. But you also have the 6 lines, so each gives you 1 generator of CP2. So you get 10 times the generator of CP2. And then you have to think about, okay, but also we have the other homology classes coming from the CP2 bars, the exceptional spheres, and how many times we intersect them. Turns out 4 times. So we get 4 times the exceptional spheres, and now it is really divisible by 2. So that means that I can use this very simple construction called the double branch cover. We already secretly use that to get from S2 to the genus 2 surface, but now we are working in higher dimensions. But the key idea is that, and this would be easier to explain with one surface. Now we have several surfaces, but it's the main idea is that I have the surface and I would like to have a new manifold which outside of the surface, in this case outside of the surface, is just known as double cover. But the surface itself will appear just once. So the way to do this locally, very easy to see, is that normally I have a disk and I would like to do the two-fold cover of the complement so that these circles still become circles in the cover. And basically I could then replace this disk with another disk, basically taking the square root in some sense. So this is called the double branch cover. You can do it in algebraic geometry. Here you are doing that. Or you could think about do it in the smooth category, also works. At the end of the day, we care about the smooth structure, maybe a little bit more, but this is a holomorphic construction. So are we okay with that? Over all of these things, over the 7, yes. So for that, you again, here, if it's just one surface, you need a condition. You need a condition that the homology class is divisible by 2. If you have 7 surfaces, you need the same condition. The sum of the homology classes of the 7 things are divisible by 2. And they are because it's 10 times the generator plus 4 times E1 plus 4 times E2 minus 4.
So you ignore D? Your branching cover over which 7 surfaces?
The 6 lines and D.
You had 6 lines.
Yeah, 6 lines, 7 points, sorry. Okay. So we constructed something, right? I hope we are okay with that. So we took the double branch cover along all of these things at the same time, and then we have something. And now our task is to understand that manifold, I guess. I said that I especially like this point, and I do. What's nice about this point is that I can take this point, and I guess even before I blow up, eventually I will blow up, but let's just think about what happens before I blow up, and then do the branch cover. What happens in CP2? I have this point, right? And I can use this point as a lookout. This is where we are right now, and we are staring at this CP2 from this point, meaning that I can choose different directions, meaning I can choose different lines going through that point, right? And see what happens. So what do? I take complex lines throughout a point, right? That would be easier to think about in C2 first, but turns out it also works in CP2. So I have lots of CP1s going through that point. How many CP1s? As many different directions I have. So I guess a CP1 verse of CP1s, or an S2 verse of S2s I have. They are not disjoint because they intersect at that point, right? Is that okay? And of course, that's not so exciting, but this is called the Lefschetz pencil of something. It's of CP2. But what we want to do is to employ this technique of looking at from this point in different directions, and now try to understand our manifold with that technique. Okay? What it means is that I'm going to choose a direction from this point. So this is my special point, and in fact, maybe it would work a little bit to be more concrete. So I will choose P to be 1, 1, 1. And because we really want to not just sort of abstractly understand what's going on, because that will not be enough, unfortunately. We want to concretely understand what's going on. So we really want to do this in a coordinate system, and we understand what's going on. So we will pick some explicit things. So So this will be the point, and A will be actually 1, 0, 0. B will be 0, 1, 0. C will be 0, 0, 1. We also have the other 3 points that are unnamed heroes in this story, but they are also important. And those other 3 points will be 1, 1, minus 1, 1, minus 1, 1, and I guess minus 1, 1, 1. And I hope you see that there is some symmetry emerging here. Namely, I really want to do this very, very symmetrically. There will be a Z mod 3 symmetry in this whole story. The Z mod 3 symmetry obviously will rotate these numbers. So we have this symmetry of x goes to y, y goes to z, and z goes back to x. That's a Z mod 3 symmetry. That's in CP2, and it also turns out, because of CP2, it's also on these lines. Okay? So that is to be very concrete. The other thing we need, unfortunately, to really make any calculations later is to specify what is the equation of D. So you can prove it exists, but it's better if you actually write it down. It will be x squared y squared plus c times x squared z squared plus z times, I guess, y squared z squared, where this thing is a third root of unity. So it turns out, in order to really, so this is something that we are going to do to be able to really understand what's happening. In order to understand that there is a genus 2 fibration, you don't need that, but in order to understand more about the genus 2 fibration, you need to specify these things. So let me just say that we have this. This is the equation for D. But coming back to what are we planning to do? So if I specify the point 1, 1, 1, then you can parameterize lines going through 1, 1, 1. This will be alpha times x plus beta times y plus gamma times z equals 0. These are lines. But, of course, I could multiply them with a complex number. It's the same line, so I don't have 3 choices. I have just 2. In fact, I have just 1 because it has to go through P, right? So these are lines going through P with alpha plus. So these are all the lines that go through P. Okay? Let's look at what happens with any one of these lines. So this is CP1, it's a sphere. Locally around the point, because we have blown up, a generic line will intersect this thing in a point, because this is exactly the direction in which you are traveling. So if I know which line we are talking about, you know what is the tangency. So this is the line how the line looks like. Okay. So my question is, how many times this line will intersect the genus, the surface we do the branch cover? So we have this branch cover, which is the 7 lines plus D, and my question is, how many times will we intersect that thing? It's not a rhetorical question. 4. This is D, right? Homework, show that this is good. It actually goes through all the points you want, and it has the required singularity around the points. Okay. So how many times it will intersect D? Well, it's degree 4, so it should intersect 4 times, right? But one of them is discounted because one of them is at P, where they are no longer intersected. This thing no longer intersects D or the other things. So we have intersecting with D 3 times. What about the other curves or the other lines? We had 7 lines, right? 2 lines usually intersect in 1 point, right? So 6 lines, maybe you would imagine 6 points, but 3 more, yes, because these 3 lines that go through the point P are no longer intersecting. I still have to worry about these other 3 lines. So this is the local picture of when I really look out to this direction, I would see a sphere, and I would see 6 intersection points of this line with the branch locus, right? So remember, if I take the sphere and do the double branch cover of the sphere at 6 points, I get a genus 2 surface. So now we do this in a higher dimension, right? But if I restrict my attention to just this pure sphere, then we are just doing the double branch cover of this sphere at branch at 6 points. So this means that that what we get out of this direction will be a genus 2 surface. I'm going to erase all of this and claim that now we have a map from the double branch cover to CP1. What is this CP1? The different directions we can go, right? And the fibers, generic fiber will be genus 2. And this is more or less CIO construction, except for one thing. These directions, so remember we had this special direction. We are going through these different directions out of P, but they are obviously at least 3 really special directions, the directions of these lines, right? And I would like to understand a little bit what's going on when I look around these directions, okay? So what happens is that these are special because originally these lines were actually part of the branch locus, right? And they are still. So what happens is that this is a -1, this used to be a sphere of square +1 because it was a hypersurface. But now I've blown it up 3 times, so now it has self-intersection -2. So it's a -2 sphere. I also have at this point and that point some spheres. I also have the divisor D, yes. Not going through this sphere, right?
No, I mean through P, and that could have also.
That's right, but that's right. You could say that's slightly strange, but not that's not that bad, because we can come back to that. Yeah. So very quickly, the story is that we have some more complicated things going on in this special direction, and we have a -2 sphere which is part of the branch locus. So what happens is that when you do the double branch cover, this sphere is still going to be the same sphere, right? It's part of the branch locus. It's not going, you're not going to double it in some sense. So there will be still the same sphere sitting inside your manifold. Now what happens is the self-intersection number will change from -2 to -1. So now it will become an exceptional sphere, which means that you can get rid of it. So you have these 3 -1 spheres in the double branch cover that are really unneeded, and we are going to just blow them down. So after you do that, turns out the story is that it's slightly more interesting, but for these 3 special directions coming here, what you will get is after you blow down the -1 sphere, you will get a torus intersecting transversely with another torus. So I mentioned that this is going to a genus 2 fibration. In a genus 2 fibration, we could have 2 kinds of singularities, reducible and irreducible. Reducible means that the homology class of the vanishing cycle is trivial. This is exactly what's happening, that could decompose a genus 2 surface to 2 tori's intersecting N1s. So you could immediately understand where these directions, that these directions give you the reducible singularities. And if you want to understand what's going on, then you also have to understand the other singularities. The T2s are in the double branch cover, right? So, yeah. So what happens is that when you still intersect these a few times, right? So I have maybe 5 more minutes. So if you are interested in this example, you can try to actually make computations. What are the things you want to compute? One is that now we have really an understanding, sort of what's going on. But what I really have is that if you give me any one of these directions, remember these directions correspond to alpha times x plus beta times y plus gamma times z equal to 0, where alpha plus beta plus gamma is equal to 0. So you could say general direction will have probably one of these things at least will not be 0. So let's say gamma is 1, that's a special case, right? And then you have something like so gamma equal to 1, and then if you know beta, you also know alpha. So basically, you can use beta to parameterize. So if you want to work this out, I did, but if you personally won't like to work this out, then it's really not that hard. So we have an S2 that corresponds to the possible choices of beta or the possible choices of directions. So this is going to be our base space, okay? And well, what we would like to understand in some sense is what's happening over every point. There is a genus 2 surface, but for some special points, this is singular, okay? So yes, because blow down, the issue is that these are holomorphic spheres. And so they have to map to a point, right? This is, if you like, don't blow down. But then you have a non-minimal Lefschetz fibration, but there are some spheres in the fiber. So you can just get rid of them and it's still a fibration. But I have 4 more minutes. Let's do that after the lectures, the question session. So how to really finish this story? Those are not that hard, but let's just discuss it. So I have fixed some beta, right? And what do I have? Well, I have a line. Okay. I have that line intersects my branch locus at 6 points. 3 of those points are really easy to find because all I'm going to do is get these other linear equations for these lines, and which are basically something like x minus z equals to 0, something like that, and just plug in, and then I would find the solutions. Is that okay? So fix beta, and then before you did any of these double branch covers, then you used to have a line going through that point, which is again a CP1, parameterize it somehow. Well, maybe don't parameterize it, that it is a CP1, okay? And what we have is that there are 6 points in this CP1. This generically, this is where this branch locus intersect that CP1. So 6 points, double branch cover of them is a genus 2 surface. Turns out it does matter where these points are if you care about the holomorphic geometry of the genus 2 curves, or maybe you don't. But it helps if you do, because then we can think about where are these 6 points. So it turns out in the sphere, if I would give you just 3 points, you can reparameterize the sphere so that these 3 points are 0, 1, and infinity. Let me do that. This is 0, 1, and infinity. How I would choose 0 and 1 and infinity? This line, intersection of this line will give 0, with that line will give 1, with line will give infinity. So you can explicitly do that. And then there is the remaining question of where on Earth are these points. Is that okay? So Z1, maybe W1, W2, W3. Where are those? Well, it turns out all you have to do is to plug into this equation and find out. This equation is degree 4, but it already meets this thing originally at this point, so I could just divide with that. I have a degree 3 equation. Luckily, there is a formula to find roots of degree 3 equations. You just do that, plug it into a computer, and for any beta, you compute these 3 points. Is that okay? So in order to see what's going on, and I'm sorry for the confusion, there are 2 spheres in this picture. If there is the sphere which is giving you the points down in the base, so this is over which you have the Lefschetz fibration, and if you fix the beta, there is another sphere here. Is that okay? Or in fact, you could say that that sphere is fixed, 1 CP1, 0, 1, infinity, but now my points depend on beta, right? And this is the sphere I want to work with. These have some special values over which there is a singularity, which you can easily solve, and I did, but you can too. Looks something like this. They are all in all 7 singularities. That is easy to find beforehand. And all you need to do is to understand what happens. These are the 7 singular points, and this is my non-singular point that I would like to use. And remember, all we have to do is to compute the vanishing cycles. So all I have to do is to parameterize everything, and then go from here to one of these singular points, and go from here to one of these singular points, and see what's going on. And what will go on is that in this picture, there are basically 2 kinds of possibilities. Either 2 of these W's will collide, that's a singularity, or 3 of these things will get very close to each other, and other 3 will also get very close to each other, and that will be another kind of singularity. So long story short, we can actually do this, and let me just give the answer and stare at this, and maybe I can then answer some questions. So So what we have, interestingly, is 6 points. 3 of them you can think about the 0 and infinity, and 3 of them are the W's, right? But right now what I'm doing is I'm fixing that point over which there are just fixed 6 points in some fashion in the sphere. Those are the 6 points. And the reducible singularities, the 3 of them that I mentioned, are all look like this. So again, remember, this is supposed to mean the sphere with 6 points, but I do the double branch cover. Which means what exactly? Which means that I'm working the genus 2 curve. So if I have a circle like this, it's 3 branch points inside, which means that the double cover of this will be a connected circle, and that is one of my circles. I have drawn one circle, but there are 3 circles all in all. How do you get the 3 circles? Just realize that there is a rotational symmetry on this. Rotate by more than 20 degrees, and then you would get the other one. 240, you would get the other one. So this is like one of the things, like Q1. And there is also 2 more pictures, and then I will be done. So the same picture again. And this is an arc, but the double branch cover, it's a curve. Let's call it R1. And actually, this corresponds to these points. You get the other 4 points by just rotating. So maybe I'm not going to draw them. But you need one more last one, and that is on here, and that looks like this. And we have this one. So this is P. And the statement is that Q1, R1, Q2, R2, Q3, R3, P is equal to these. So it's equal to identity if you want closed surfaces, or equal to the positive Dane twist around these 3 points. This would be delta 1, delta 2, delta 3. And you have to use this rotation to get Q2. So this. So maybe this was too fast. But there is nothing inherently hard in this at all. So you can do this by yourself if you really want to. But the bottom line is that there is this really interesting fibration. There was a paper by Boykur and Korkmaz that reverse engineered a relation like this, so a force-free relation. And they conjecture that that comes from Xiao's fibration. So that is a perfectly valid approach, that you just try to come up with a relation. But what I try to demonstrate in these lectures is that you can actually, if you are willing to understand a little bit of algebra geometry, actually don't need that much, then you can just directly do this and find the actual vanishing cycles. So if you go through this argument, you will prove that this relation is true. But if you don't want to go through this, you can just take this relation and try to double check. And I did that too, so it's not checked more than one way. Okay, thanks for your attention.
How do you know the total space from this? Did you compute the total space as S2 cos T2, blown up 3 times?
So, Xiao already proves that. So I don't, and so this is Xiao's construction. The new thing is that we made this very explicit. So I should say that Xiao has a really excellent construction that I urge you to read, because what he does is starts with an elliptic curve and the number. Elliptic curve is just a complex torus, and the number d, and constructs for you a very nice genus 2 fibration. Now, in this case, it might not be obvious, but I deliberately chose a Z-mode 3 symmetry in this picture. So that means that there are all kinds of Z-mode 3 symmetries everywhere. Turns out this corresponds to the elliptic curve that has a Z-mode 3 symmetry. So this is this. Don't be too intimidated by somebody says elliptic curves. All they say is a complex number, right? So I need 1 and the complex number z, and I divide C2 with the parallel translation of 1 and z. I'm choosing z to be the third root of unity, and that is a very special elliptic curve. And turns out this construction corresponds d equal to 3 and this elliptic curve. The topology of what you get doesn't depend on this elliptic curve, so you always get the same thing. And so already proves that this is CP2. Sorry, S2 cross T2 blown up 3 times, so I don't have to reprove that. But, of course, you can use these things to compute the fundamental group. What you get an extra from this is the Z-mode 3 symmetry. There's a complete Z-mode 3 symmetry on this fibration, but you don't see the Z-mode 3 symmetry on this last thing because that you have to go from here to there, and exactly how you do that, that's not completely symmetric. But if you put P somewhere else, then you can have to rotate this P by 120 degrees. What other things I could say? Yes?
And so from those 3 lines that were meeting at the top,
Yes.
we blew down and we got this 6 tori, right? Like
Yes, yeah.
Is that the 6 singular fibers?
These are the 3 singular fibers, right?
Yeah, just 3.
Right, so 3 of the 7. There are 7 singular fibers because you see 7 letters here. And the reducible ones,
So those 3 are the Qs.
the Qs, yes. I should have called these Rs and these Qs, but too late. Yes, so these are directions in which the genus 2 curve decomposes as a nodal 2 toris intersecting each other once.
But I then don't see where the other singular is.
Yes, because I didn't have time to explain that. So, so how do we know that there are other singularities? How do we get the other singularities? I already erased my beautiful picture, but we have these different lines through P, and this is I do before I blown up or anything. So that you don't have to. You can do that later, but right now I don't yet blow up. So now I'm really working in CP2, and now I have my curve, which I already erased, but it's a very nice equation. So D usually intersect this at 4 points. One of them is P, right? So this is the usual thing, 4 points. Hope it's 4. But for some special values of directions, not this one, but maybe this one, it's tangent. So it means that 2 of the W's collide. And if you do the double branch cover, then you see that now you have something that has a singularity at the point when you collided. These 2 points will give you just 1 point, and this is really this corner point. And so in order to really do this explicitly, which I like because then you see what's going on, so I have an explicit parametrization of S2 with complex numbers. So it means that I could try to solve where are these directions when this happens, and where are the 4 directions when it's tangential. You just have to plug into the equation and solve it. Turns out this S2 has Z-mode 3 symmetry, so this is my reference point, which is symmetric under the Z-mode 3 action, and the opposite point will be exactly one of the special directions, and you still have to choose the other 3. But you can solve for this. Turns out what you have to do is to intersect that equation with some really complicated line, like, I don't know, x plus y plus z equals 0 or something like that. And then you will see actually the intersection point. Yes?
So you parameterize, you see these points colliding.
Yes.
In this picture, how do you get the vanishing cycle? How do you know which
Right, because I'm doing this, right? I have this picture, right? Sorry. I have this picture to begin with, right? Where this is 0, this is 1, this is infinity, and I have 3 more points, right? And this is what's happening here. So now I plug it in a computer and see what happens with these points. They will be moving. But then at this, eventually, something has to happen when you approach the singularity. And what will happen is that these 2 points will start moving and literally span this direction, which is not enough after a little thinking to see what's going on. So what's happening, and I should like to emphasize that there are lots of genus 2 curves. How many? Basically, if you just want to count the parameter space, 6 points in CP1. So 3 of these you can fix. The rest of the 3 could move wherever. So 3 complex dimension. Okay. Okay. So agrees with 3G minus 3. But in this case, you just see a 1-parameter family of these things that sort of happen to come in this construction. We don't really care so much about what are the holomorphic structures, really, but we just want to see what happens topologically with these points moving. Or you can also directly do the monodromy. And instead of going to the singularity, if you don't like that, I did that first, just go around and then come back. And then it's actually more manageable because in a computer, that is more, you don't have to divide by 0 at some point. So you don't have really singularities, you can really keep track. Now, one other thing I wanted to mention, sorry, very, very quickly, that there is this D. You don't see that D at all in this picture, but I can tell you what D represents. So there is this 3-dimensional complex parameter space of genus 2 curves. And what Xiao does is fixes this D and fixes also his elliptic curve. So there are 2 inputs to this construction. Number greater than or equal to 2. Let's say greater than or equal to 3 because 2 is really special. And this 1, and they have to fix that Z as well. And that says, well, let's take all the genus 2 curves satisfying that they admit a holomorphic map from here to that T2, right? It has to be holomorphic. Turns out not too many such things exist. There's a complex 1-parameter family of such curves. And basically what we are doing is taking all of them. So you don't see that from this picture, but the kind of complex curves you get here are very special. Just only those when you have this degree 3 map from here to this very special elliptic curve. The elliptic curve has symmetry, so you could imagine there is some kind of symmetry in this whole picture as well. So for D equal to 3, you don't have to do that because Xiao luckily also worked out this alternative construction, which is much more manageable. But if you want D equal to 4, which I wanted, then this picture is just not going to help. And then you have to employ another trick, which I'm not going to discuss. It's already over time. But if you are interested, I can tell you, and I also plan to write that down at some point. So it turns out you can really do this very, very concretely and understand this. And then you can ask yourself, OK, so what have we achieved? Well, on face of it, not too much. We get T2 cross S2 now blown up 3 times. And there's a different fibration over the sphere. But remember what I said, you can use this as building block. So, and other people have already done that, but you can also do that. So now we have 2 interesting fibrations over S2 with genus 2 fibers. Just mix and match, choose one or the other, and you can do all kinds of interesting things. To circle back to what András said, that sometimes you can do things symmetrically, and then divide with the Z mod 2 action and get something interesting. Turns out, yes, you can do that too. You can take this example, and this is a joint, will be in a joint paper with András and Inancs Bajkur, and then divide with, and just double it in such a way that the fundamental group is now trivial, and then you still would have this Z mod 2 action. So you could actually get an exotic CP2 blown up 7 times very easily, and if you want to make sure that there is a Z mod 2 involution, you can also get some of this definite intersection form with Z mod 2 fundamental group. And I should also say that this is one of many tricks. There are other tricks, so you don't always have to study genus 2 fibrations. Last thing, why on earth you should care? So there are these various interesting conjectures that András mentioned. One is there an exotic CP2? Is there an exotic S4? We will not be able to touch S4 with this, but if you want X2 cross S2, CP2 ones, progressive and CP2, you could ask, is there maybe a symplectic version which is exotic? Symplectic, the symplectic form omega, d omega is 0, omega square is the volume form. Turns out these examples will be symplectic. So for free, you get symplectic things as soon as you satisfy some mild conditions on the Lefschetz fibration. Homology cluster of fiber is non-trivial. So is there an exotic CP2, an exotic symplectic CP2? We don't know, but if there is one, there is a theorem of Donaldson that tells you that after sufficient many blow up, there will be a Lefschetz fibration. It's not going to be a genus 1 Lefschetz fibration, that we know for sure. We also know it's going to be a genus 2 Lefschetz fibration. But it might be, who knows, a genus 7 Lefschetz fibration. So you should study this because it's possible and in fact quite likely that you can find interesting exotic manifolds by just using Lefschetz fibrations or Lefschetz fibration combining with other tricks like surgeries along tori's or other things. Thank you very much, and I will be